Okay guys, welcome back to our channel. So our topic for today is rotation. So rotation is a little bit similar to rectilinear translation, but our variables are omega, theta, and alpha. Okay, so in rectilinear motion, our variables are v, s, and a. So same here. So we have, instead of v, we are going to use omega. So this is linear velocity and this is our angular velocity. Then acceleration is a in rectilinear motion, but here we have alpha. And the position or displacement, instead of using s, so we have theta or the angular displacement. So we can relate these two equations by using this equation. So same in this table, so we have is equal to r theta. If we differentiate both sides in terms of time, so we have ds over dt equal to, so our r is constant. So r multiplied by d theta over dt. Okay, and then from that, so ds over dt is velocity and d theta over dt is our omega. So this equation will become v is equal to r omega. So if you still remember this equation, this is also equal to 2 pi rn. For n here is the angular velocity in revolution per minute. This is in radian per second. Again, if you want to relate these two, we can differentiate this equation. So we have dv over dt equal to r d omega over dt. So the omega over dt here is our angular acceleration, and dv over dt is our tangential acceleration. So we have this equation. Now for the normal acceleration, that is simply r omega square. So we know that the tangential acceleration is here and the normal acceleration is here. So our s can be visualized based from the path of our object. Anyway, the path of our object or the particle for this topic is circular. Okay, so assuming here we have a particle or object starting at this point. So from this point up to this point, the arc distance is here. So arc distance is denoted by s. So now if we want to derive this equation of rotation, we can use this equation and then use the relation between the two. So here we have velocity, so we can replace this by this one. So we have r omega. Then for the initial velocity, we will just put a subscript of 0 for the angular velocity plus our acceleration. So this one, that is r alpha multiplied by time. Okay, so this is our a sub t, this is our VO, this is our final velocity. So from that, since r is common, we derive the equation omega or the final angular velocity is equal to omega sub o plus alpha t. Okay, so same manner with these two equations. We can change s by r theta, then v sub o by r omega sub o. Then for acceleration again, that is r alpha. Then for v, again, we have r omega, v sub o, r omega sub o, and then a again is r alpha. And then for s, we can replace that by r theta. So we can derive this equation. Then next, we also have the rotation with variable angular acceleration. So this is somewhat similar dun sa ating topic na rectilinear motion with variable acceleration, wherein we have 4 cases. So here, instead of using s, we will use theta, and a is alpha, and v is omega. Okay, so same procedure or the same steps yung gagawin natin pagsosolve dito sa rotation with variable angular acceleration. So let us solve some problems. So our first problem from the book of Ferdinand Singer, problem 1202. A flywheel 6 feet in diameter. So we have diameter equal to 6 feet. Accelerates from rest. So meaning our initial velocity, we have 0 at the constant rate of 4 revolution per minute per second. So if you will analyze this given, so revolution per minute per second, this is our acceleration. So required compute the normal and tangential components of the acceleration. So we have a sub t and a sub n. So that is after 10 seconds. So we have another given time that is 10 seconds. So how can we solve now the tangential and normal components of acceleration? So the formula for the tangential acceleration is equal to r alpha. Okay? And then for normal is simply r omega square. So from the given, we already have alpha. But how about our omega? So take note, our omega here should be at the end of 10 seconds. So we have omega sub O, which is equal to 0. So how can we solve now for the final angular velocity? So from our equation, we have omega is equal to omega sub O plus alpha t. And we have omega square plus omega sub O square plus 2 alpha theta. So based from the given, we can solve the final velocity or angular velocity using this equation. So we can use omega is equal to omega sub O plus alpha t. So accelerates meaning this is positive and this is 0. So t is 10 seconds. So let us solve first for the tangential acceleration. So solution. So this is for a sub t. So from the formula, a sub t is equal to r alpha. So we can now substitute r and alpha. So r is, since we have diameter of 6 feet, so our r is simply 3 feet. So assuming this is our flywheel, so we have r is 3 feet multiplied by our alpha here, since the given is in revolution per unit time, so we need to convert that into radian per unit time or radian per second square. So this is for revolution per minute per second. So we cannot multiply these two, so let us convert radian to revolution. And at the same time, minute to second. So revolution, so we have 1 revolution, that is 2 pi radian, multiplied by 1 minute per 60 second. So revolution will cancel, and at the same time, minute. So our unit here is in feet per second square. So we have 1.257 or 1.26. The next for a sub n or the normal acceleration. So let us use our equation. A sub n is equal to r omega square. Omega, or the final angular velocity, can be solved using this equation. So we have alpha t with omega sub O equal to 0. And then for our alpha, we have 4 revolution per minute per second. But again, we cannot multiply that directly to our time. So we need to convert that again into radian per second square. So this is equal to this quantity. So 4 revolution per minute. Then for time, that is 10 seconds. So our unit now is in radian per second. Substituting this omega into this equation, so we have r is 3 feet, then omega 4.19 radian per second square. So the answer here for the normal acceleration is 52.67. So we are done with our first problem. So let us proceed to the second problem. So from the book of Ferdinand Singer again, problem 12. The rim of a 50-inch wheel on a brake show testing machine has a speed of 60 miles per hour. So that is an initial velocity or V sub O when the brake drop. So meaning we have a rotating flywheel with an initial velocity of 60 miles per second. So the given here is actually a diameter. So this is D. It comes to rest after the rim has traveled a linear distance of 600 feet. So linear distance meaning that is our S. Then it comes to rest. So ibig sabihin, ang final velocity natin dyan ay 0, including our angular velocity. What are the constant angular acceleration and the number of revolutions the wheel makes in coming to rest? So constant angular acceleration, so that is alpha. And the number of revolution, so meaning that is theta. So based from this given, how can we solve now for alpha and theta? So first of all, let's take a look yung equation na may v tsaka yung s. So yung v, that is r omega, and then yung s, that is r theta. So meaning, we can solve for omega and theta. So if we have initial velocity, so meaning we can solve also for initial angular velocity. Okay, so we can now solve for theta using this equation. So let us solve first for theta. So using this equation, wherein we have S 600 feet, our R is 25 feet. Or we can divide yung given na 50 inch by 2 and then convert that into feet to make the unit consistent. Okay, so that is equal to 2.083 feet for the radius. So this is 2.083 feet multiplied by our theta. Take note, if we use only theta here, then simplify or solve this to yung S over R, the unit of theta is in radian. So that is 288.05 radian. Then since revolution ang hinahanap, so we need to convert this into revolution. So using our conversion, 2 pi radian per revolution or 1 revolution, we can solve for theta in revolution, which is equal to 45.85. Next unknown, we have the angular acceleration. So again, from our equation, the equations with acceleration here are these three. So again, based from the given, what we have is v, s, omega, or the final angular velocity, and our radius. So if you will use equation 1, we don't have actually your time. So we cannot solve for the acceleration. Then for the second equation, so we don't have, again, your time, although we have your theta, and although we can solve for the initial angular velocity. And then for third equation, we can solve for omega sub o, then our final velocity or angular velocity is 0, and we have your theta, which is equal to 88.05 radian or 45.85 revolution. So meaning we can solve for the angular acceleration using this equation. Now if we want to use negative here, so that's okay since our object or the flywheel is coming to rest. Okay, so let us solve for alpha using of course yung theta and then yung ating omega or the final angular velocity. So this is 0, but initial angular velocity here is not given. We can use this equation. We have an initial velocity and the radius. Since the given is in miles per hour, we need to convert this into feet per second to make our units consistent. So let us convert this 60 miles per hour. So this is 88 feet per second. So we can now use this 88 feet per second to solve for omega sub o. Or we can simply substitute omega sub o, which is VO over R, to our equation, wherein VO is equal to 88 feet per second and R is equal to 25 inches or 2.083 feet. So V sub O is 88 feet per second over our R is 2.083. So take note, again, this quantity is from this equation. So this is in feet. And then again, take note, if you have feet per second over feet, so the unit for angular velocity is radian per second. Then radian for the theta, the unit for the angular acceleration is always in radian per second square. So solving for alpha here, so that is negative. So this is equal to 3.098 or 3.1 radian per second square. So next problem, this is under variable acceleration. So we have a given equation, theta is equal to 2t to the fourth minus 30t square plus 6. So that is an equation for theta, where theta is measured in radians and t in seconds. Compute the values of angular velocity and angular acceleration at the instant when t is equal to 4. So angular acceleration, or that is our alpha. And our time is 4 seconds. So this is under, again, your rotation with variable angular acceleration. So the method that we are going to use or techniques are similar to these topics wherein we have 4 cases. So the first problem is actually case 1. So we have theta and t. So what we need to do is just to simply differentiate the given equation with respect to time to solve for omega. Okay, solution from omega is equal to d theta over dt, or that is equation number 1 for this equation. So this is equal to differentiate the given equation with respect to time. So we have 8t cubed minus 60t. So at 4 seconds, our omega is equal to 8 multiplied by t is 4. So cube minus 60 multiplied by 4. So our omega here is 272. So the unit is of course in radian per second. So next we have alpha. So alpha can be solved using our differential equations of rotation or our equation number 2 or this equation. So we have alpha is equal to d omega over dt. So let us differentiate our equation for omega. So ito yun. So that is 24t square minus 6t. Then add t is equal to 4 seconds. So alpha is equal to 324 radian per seconds square. So last problem for this topic. So we have problem number 12.14. The rotation of a flywheel is governed by the relation omega is equal to 4 square root of t, where omega is in radians per seconds. Theta is equal to 2 radian when t is equal to 1 second. Compute the values of theta and alpha the instant when t is equal to 3. So the required here are alpha and theta at t is equal to 3 second. So what do we mean by these two given? The 2 radian and the 1 second for time. So t and theta here will be used for the integration process. So anyway, this is case number 3. The given is angular velocity and time. So in our rectilinear motion with variable acceleration, here we have case 3, velocity and time, or the velocity is given as a function of time. So in this problem, we have omega is equal to square root of t. Okay, so to solve that, based from these techniques is to differentiate to solve for the acceleration. And then integrate to solve for the displacement. So meaning, let us differentiate first the given equation to solve for the acceleration. So let us differentiate the given equation to solve for the acceleration. So we have d omega over dt. So again, differentiate this equation. So that 4 square root of t can be written as 4t raised to 1/2. Then we can use the power formula to solve for its differential. But we can also use the formula to solve for the differential with a radical sign, wherein the derivative of, say for example, x is equal to 1 over 2 square root of x. So any of the method of differentiating square root of t will give the same result. So let us use this one. So this will become 4 multiplied by 1 over 2 square root of t, or this is equal to 2 over square root of t. Then at t is equal to 3 seconds, we can solve alpha using this equation. So we have 1.155 radian per second square. Next, so from this differential equation of rotation, which is omega is equal to d theta over dt, we can now solve for theta. So substitute the given equation for the omega. So 4 square root of t. So d theta is equal to 4 square root of t dt. Then integrate both sides. Okay, so we can now use the given theta and t. So this will be our lower limits. Okay, so theta 2 radian. So we need to put that here. Then for t is 1 second. Then for our lower limit, so for d theta, we can put that as theta, since this is the unknown. Then if we want to derive first for the equation, we can put the upper limit for this integrand as t, or t here is equal to 3 seconds. So let us derive first our equation. So this will be theta. Our limit is from 2 to theta equal to, so the integral of this is simply 4 multiplied by t raised to 3 halves over 3 halves. So the limit is from 1 to t. So theta minus 2 is equal to 8 over 3 t raised to 3 halves from 1 to t. So again, we can just put 3 seconds for t. Okay, so if we want to derive this equation, so this will become 8 minus 2 equal to 8 over 3 t raised to 3 halves minus 8 over 3 multiplied by 1 raised to 3 halves. So let us simplify this equation. So we have now this equation for theta. So let us now substitute t is equal to 3 seconds. So this is equal to 13.19. So take note here that the unit of theta is in radian. That's all for this video. Thank you for watching.